Today we're going to learn how to figure out the pH of different ionic compounds. We call ionic compounds in chemistry salts. So what happens to different salts when we dissolve them in water? So we've been talking lots about equilibrium in this unit, and this is a place where definitely equilibrium is involved. So deciding whether something is acidic or basic when it's dissolved in water, especially when it comes to ionic compounds, comes right down to, does a reaction actually occur between water and the dissociated ions of the salt? Do they interact and change the pH, or do they not interact and stay neutral? So what we're going to do is look at this only from a qualitative point of view. We're not going to do any calculations. That's the next level up in this area of chemistry. Just looking at them, we're going to predict, is the salt acidic, basic, or neutral? So what we're going to do are examine the two ions in an ionic compound. The cation, remember, is the positive ion, and the anion is the negative ion. We're going to look at them separately and look for their conjugate acid-base pairs and try and figure out what the pH of a solution is. So we're just basically going to walk through 4 different scenarios in the lesson today and apply a lot of the knowledge that we've learned about acid-base theory and equilibrium along the way. So we're going to start off with sodium chloride. Here, our positive ion is always the first ion, sodium, and the negative ion is the second one, our chloride ion. So here we want to take note, cation is positive sodium, and the anion is negative chloride. We're going to look at each of them separately and write down a theoretical reaction on paper. What if they were to interact with water? What would happen? So remember, water, before we actually start this, water is made up of HOH. So there's a hydrogen ion and a hydroxide ion. So the two ions in the salt have to choose which ion they're going to interact with, the positive hydrogen or the negative hydroxide. So if we did our example with the sodium ion, it's positive, it's going to attract, in theory, the negative hydroxide. So if it were to interact with water, we would get NaOH, and then the other ion left over would be hydrogen. Now, when we take a look at this, remember, we're just writing this on paper. Is this actually plausible or not? Does it make any sense? What we want to look at is what we make, the compound or ion, and decide, is it an acid or a base, and talk about its strength. Is it strong or is it weak? Looking at this sodium hydroxide, hopefully you recognize right away, this is a base. And then we have to think about our strength of acids and bases. Is this a strong acid? Or sorry, is this a strong base or a weak base? This one here we know is definitely strong. And remember what we said about strong bases? They completely dissociate in the presence of water. So is there any chance that this is actually going to reform? No, it's not going to happen at all. So this reaction actually doesn't happen. And what we can say here is the sodium ion does not interact with water. Then we're going to do the same thing with the chloride ion. So chloride ion plus water, what's going to happen next? Because this is a negative ion, it's going to attract a positive ion, and the positive ion from water is hydrogen. So we get HCl, and the other ion that would be left over is the negative ion from water, which is hydroxide. Then we're going to do the same thing again. Take a look at what we made. Acid or base? Definitely an acid. Strong or weak? Hydrochloric acid is strong. And again, then we take a step back and say, is this possible that we can reform a strong acid molecule in the presence of water? No, definitely not. So this is not possible either. So we can conclude chloride does not interact with water. Now, in this scenario, neither ion interacts with water. If neither ion interacts with water, then we can say that this salt, the sodium chloride, is neutral. It has a neutral solution with a pH of 7. So here, if you were asked, what's the pH of sodium chloride? Is it acidic, basic, or neutral? You would walk through the process like we just did, analyze the sodium ion, analyze the chloride ion, and if you find that both of them don't interact, you get a neutral solution. You only get the pH of water, which is 7. On the last page of our lesson, if you have them printed off, there's a chart. So after we finish each example, we're going to flip to this chart and fill in some information. So the first example, we're going to fill in this first box in here. The example that we saw is sodium chloride, and we said it's a neutral solution. What do we do with the other part in the chart up here? Reaction with water. Here we're going to write neither ion reacts. And if we look at the rest of the table here, the cation from a strong base here, we had sodium, which was sodium hydroxide, anion from a strong acid, chloride, which comes from hydrochloric acid, which is a strong acid. So that's where they fit into this part of the table. So we'll come back and fill this in along the way. And then at the end, you'll have a really good study sheet for this part of the unit. So now what we're going to do is take a look at some other examples so you can see an example of where something would be acidic or where something would be basic. So what I want you to do and try, see if you can write out the equations first for sodium phosphate, and we'll walk through that one together. So take a moment, pause your video, see if you can write out the equations. And when you're ready to check, unpause, and let's take a look together. So now let's take a look at the first example. So our first example, sodium phosphate. And I've already got the first answer in here because we just saw it. In sodium phosphate, there's two ions, the sodium ion and the phosphate ion. Sodium ion, even though it's paired up with a different anion here, still is the same scenario as before. Sodium interacts with water, it would gain that hydroxide ion, but we know that's not plausible because sodium hydroxide is a strong base, and that's not going to work for us. Let's take a look now at the phosphate ion. So here we've got the phosphate ion. If the phosphate ion gains one hydrogen, it makes the hydrogen phosphate ion. And you'll be left with hydroxide here. So when we take a look, we look at what we made here. Is this an acid or is it a base? We don't see hydroxide in here or an ammonia group, amino group. So we know this is going to be an acid. And it's not one of our 6 strong acids, so we know it must be weak. So if that happens, that means we get an equilibrium establishing here. We're making something weak, so we're going to see a little bit of everything establish itself. So then we have to decide, how did this form and what is the phosphate ion doing? So if we look, phosphate gains a hydrogen. Anything that gains a hydrogen, we know is acting like a base. The other clue that the phosphate ion's acting like a base here, you get a production of hydroxide ions. This is a basic ion. So in this question, if we were going to decide whether it's acidic, basic, or neutral, sodium does nothing, so we can just ignore it. But here, the phosphate does play a role in the pH, and it does interact with water. So here we can say a basic solution results. So then we can conclude this is a basic salt. All right, let's try another example. So again, I want you to try this one out first before checking your answer. So next up is ammonium nitrate. So here we've got two ions. There's an ammonium ion and a nitrate ion. So let's see if you can just write down some basic equations, and then we'll check the pH together. So when you're ready to unpause, come back and we'll check together your answers. Okay, let's see what you've got. First one I've already got done here for you. With the nitrate ion, nitrate is negative, it will gain a hydrogen and make nitric acid. Nitric acid is one of those 6 strong acids. Anytime you make a strong acid or base on paper, we can basically say this is not possible. It's not going to happen. So we can just cross it out right away and move on to our other ion and take a look. So let's look at what's happening with the ammonium ion. Now for this one, because it's ammonium, it's more applicable with Bronsted-Lowry theory, and if you see something with ammonium, I would approach it this way. So let's take a look. The ammonium ion would interact with water, and here it's going to lose a hydrogen and make ammonia. Ammonia here we have to decide, is it acidic or basic, strong or weak? This one here we know is a base, but it is not strong. It is a weak base. Ammonia is a characteristic weak base. So again, we're going to kind of backtrack and do the same thing that we just did for the previous example. What's going on with ammonia? Ammonia loses a hydrogen. Anything that loses a hydrogen is acting like an acid. Other clue here, we've got H3O+, which is, we know, hydrogen ion, which we know is acidic. So this ion here is making the conditions acidic. So when we take a look here, we've got an ion that doesn't interact. We've got one ion that does interact, and this time it's making an acidic solution or acidic scenario. So here we can say NH4NO3 is acidic. Now let's go, before we do the last problem, go and fill in the rest of our chart for the last 2 examples, and then we'll deal with our final scenario, which is the one that's the most complicated. So let's take a look. We can fill in the one that we just did first if you like. That was down here, ammonium nitrate. We have a cation from a weak base, that was the ammonium. And then we've got the anion from a strong acid, which is nitrate. Here we said the cation interacts with water. That was our ammonia here. And here we said our solution ends up being acidic. The previous example would fill in the top right-hand corner for our box. So that one was with sodium phosphate. So with sodium phosphate, the sodium ion is the cation from a strong base, just like the previous example. The anion is the phosphate and it came from a weak acid. Here, the anion interacts. And that makes your solution basic. Okay. Now we've got one more example we haven't gone through yet. So let's go back. And the last one we have to tackle is ammonium nitrite. So I want you to do the same thing again. See if you can write out the equations for ammonium nitrite. And when you're ready to check, unpause your video and see if you're on the right track. So let's take a look at both of those equations. I'm going to put both of them up at the same time so we can take a look at them together. Okay, so if we look at the first example, this is the same scenario we just saw. This is acting like an acid because we're making a weak base. So this ion, ammonium, is interacting to make an acidic condition. Down here with the nitrite ion, give ourselves some more room. If we look, nitrite is forming HNO2, nitrous acid. Nitrous acid is a weak acid. Since that ion's accepting a hydrogen, it's acting like a base. So this is a different scenario. Here we've got two ions, both of them are interacting with water. So both of them will affect the pH. Which one is going to win? We can't just decide arbitrarily, we need some numbers. So guess what we're going to have to do? We need to look up a Ka value for ammonium. And then we need to look up a Kb value for nitrite. If you remember, there are Kb values on page 746 in your textbook. And for Ka, it's on page 747. I would recommend taking a look and see if you can find the Ka and Kb values in the appendix of your book right now. So if you don't have it handy, pause it, go grab it, take a look, and see if you can find it. After taking a look at the appendix, hopefully you found that there is a Ka value for the ammonium ion. It's 5.6 times 10 to the negative 10. But did anyone have any luck finding the Kb value of the nitrite ion? You shouldn't because it's not in that table. But what you might be able to find if you look for Ka values, you will be able to find a Ka value of the nitrous acid in the table. So if you scan down that table, you will find a Ka value for nitrous acid, which is 5.6 times 10 to the negative 4. Now we still need the Kb value. We need to compare the Kb value of nitrite to the Ka of the ammonium. We have to do that. But how do we get the Kb value? Well, nitrite and nitrous acid, this is our conjugate acid base pair. Probably wondering what we were going to do with this back when we learned about Bronsted-Lowry theory. Well, here's one place where it comes in. These are conjugate acid base pairs. There's one more formula that deals with conjugate acid base pairs, which we haven't seen yet, which is Kw is equal to Ka times Kb. This only works for conjugate acid base pairs. So if we want to find the Kb value and we have the Ka of its conjugate pair, we can use this formula and rearrange and solve for Kb. So what we would do, Kb is equal to Kw over Ka. Kw is always 1 times 10 to the negative 14. We're going to divide it by that Ka, 5.6 times 10 to the negative 4. And we get the Kb equal to 1.8 times 10 to the negative 11. That's for nitrite. Now, back up at the top, we put in our Ka for ammonia. The Ka for the ammonium ion is 5.6 times 10 to the negative 10. So I've got them both written down here just for easy reference. After we've done all of this work, essentially these are the two numbers that we need to compare. So is this salt acidic or basic? That's still what we're trying to find out after all of this work. Ammonium nitrate, acidic or basic? Here you're going to compare the Kb to the Ka. Which number is larger? Here, the Ka is greater than Kb. And if the Ka is larger, that means more of those ions will dissociate, and you're going to get an acidic solution. So you can say NH4NO2 is acidic. Lots of work just to get to this answer. So let's go and fill in that last part of the table. And there's two other scenarios which we haven't got to for this bottom corner, but we'll list them here. So what happens? Both ions interact. So what happens to the solution? If Ka is greater than Kb, we know we get acidic conditions. If Kb happened to be bigger than Ka, we didn't see this, but if that was the scenario, it would be basic. You could also encounter a place where they're both equal. That would give you neutral solution, although that's probably not very likely that that's going to happen. And just a reminder here, Ka and Kb must be conjugate pairs. That's the only way this is going to work. So hopefully you found that helpful to go through qualitatively and decide whether something's acidic or basic. There's some problems to work through in the textbook and also a demo online to work through and help see in action what happens when you dissolve some salts in water and test their pH. So try those out, and hopefully after all that practice you'll be a pro at figuring out pH of your salts.